The requirement for medium voltage shielded cable depends on the specific standards and regulations applicable to the project. In general, medium voltage shielded cable is not mandatory for 4160 volts applications, but it is recommended for certain circumstances. Firstly, when the cable is running parallel to other cables carrying significant current. Secondly, when the cable is in an environment with high electromagnetic interference, or EMI. And thirdly, when the cable is exposed to external mechanical damage or stress. In your case, the transformer will be located next to the amp card starter. Since the cable run is short and the environment is likely controlled, medium voltage shielded cable is not strictly required. However, it may provide additional protection against EMI and ensure reliable operation of the motor starter. Since the transformer lugs are not suitable for stress currents, you will need to use alternative termination methods. You can consider using cold shrink connectors or slip-on connectors that are specifically designed for medium voltage applications and meet the necessary insulation and surge withstand ratings. Any modifications to the transformer must be authorized by the manufacturer. Modifying the lugs without proper authorization could void the warranty and compromise the safety and reliability of the transformer. It is best to consult with the manufacturer or a qualified electrician to determine the appropriate termination solution. Based on the information provided, it is not strictly required to use medium voltage shielded cable for the application. However, it may be beneficial to consider using shielded cable for enhanced protection against EMI. Consult with a qualified electrician or the equipment manufacturer to determine the best course of action and ensure compliance with applicable standards. Now let's delve deeper into the considerations for using medium voltage shielded cable with a 4160 volts transformer. While not always mandatory, shielded cable offers significant advantages in certain scenarios. Firstly, consider the proximity to other cables. If the cable run from the transformer to the motor starter is close to other cables carrying substantial current, the electromagnetic fields generated by those cables can induce noise and interference in the unshielded medium voltage cable. This interference can disrupt the operation of the motor starter, leading to malfunctions or even damage. Shielded cable, with its grounded conductive layer, effectively blocks these electromagnetic fields, ensuring a cleaner signal and more reliable operation. Secondly, evaluate the electromagnetic environment. If the installation is located in an area with high levels of EMI, such as near radio transmitters, industrial equipment, or other sources of electromagnetic radiation, shielded cable becomes even more crucial. The shield acts as a Faraday cage, preventing external electromagnetic fields from interfering with the signal within the cable. Thirdly, assess the risk of mechanical damage. If the cable is exposed to potential physical damage, such as from abrasion, impact, or crushing, shielded cable provides an additional layer of protection. The shield can help to prevent damage to the insulation and conductors, reducing the risk of electrical shorts or failures. Now, let's explore the available termination methods for medium voltage cable, especially when stress cones are not feasible due to lug size limitations. Cold shrink connectors are a popular option for terminating shielded cable. These connectors utilize a pre-expanded rubber or silicone sleeve that is installed over the cable and then allowed to shrink down, creating a tight seal and secure connection. Cold shrink connectors are relatively easy to install and do not require any special tools or heat, making them a convenient choice for many applications. Slip-on connectors are another alternative. These connectors consist of a pre-molded insulating body that is slipped over the cable and then secured with a mechanical clamp or compression fitting. Slip-on connectors offer excellent insulation and surge withstand capabilities, making them suitable for demanding medium voltage applications. Regardless of the termination method chosen, it is essential to ensure that the connector is properly rated for voltage and current of the system and that it is installed according to the manufacturer's instructions. Improperly installed connectors can lead to insulation failures, electrical shorts, and even fires. Now, let's discuss the importance of consulting with the transformer manufacturer before making any modifications to the transformer lugs. Modifying the lugs without proper authorization can void the warranty and compromise the safety and reliability of the transformer. The transformer manufacturer can provide guidance on the appropriate termination methods for the transformer lugs and can also recommend suitable connectors that are compatible with the transformer's design. In some cases, the manufacturer may offer alternative lug options that are specifically designed for use with shielded cable. Consulting with a qualified electrician is also crucial. A qualified electrician can assess the specific requirements of the installation and can recommend the best course of action for ensuring compliance with applicable standards and regulations. The electrician can also perform the cable termination and testing to ensure that the system is installed safely and correctly. In summary, while medium voltage shielded cable is not always mandatory for 4160 volts transformer applications, it is highly recommended in situations where there is a risk of electromagnetic interference, mechanical damage, or proximity to other cables carrying significant current. When stress cones are not feasible, cold shrink connectors or slip-on connectors can be used as alternative termination methods. However, it is essential to consult with the transformer manufacturer and a qualified electrician before making any modifications to the transformer or selecting a termination method. Furthermore, it is important to understand the National Electrical Code, or NEC, requirements related to medium voltage cable installations. The NEC provides specific guidelines for cable sizing, insulation, grounding, and termination. Adhering to these guidelines is essential for ensuring the safety and reliability of the electrical system. For example, NEC Section 310.16 provides ampacity ratings for various types of cables based on their size, insulation, and installation conditions. NEC Section 310.10 provides requirements for cable grounding and bonding. NEC Section 400 provides requirements for flexible cords and cables. In addition to the NEC, there may be other applicable standards and regulations, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide more detailed guidance on specific aspects of medium voltage cable installations, such as cable testing, termination, and maintenance. Let's talk more about cable selection. When selecting medium voltage cable, it is important to consider the following factors. Firstly, voltage rating. The cable must have a voltage rating that is equal to or greater than the system voltage. In this case, the cable should be rated for at least 4160 volts. Secondly, ampacity. The cable must have an ampacity that is sufficient to carry the load current. The ampacity of the cable is determined by its size, insulation, and installation conditions. Thirdly, insulation type. The cable insulation must be suitable for the operating temperature and environmental conditions. Common insulation materials for medium voltage cables include cross-linked polyethylene, or XLPE, and ethylene propylene rubber, or EPA. Fourthly, shielding. If shielded cable is required, the shield must be properly grounded to provide effective protection against EMI. Fifthly, environmental conditions. The cable must be able to withstand the environmental conditions to which it will be exposed, such as moisture, chemicals, and UV radiation. Now, let's discuss the grounding of the cable shield. The cable shield must be properly grounded to provide effective protection against EMI. The grounding method should comply with the requirements of the NEC and other applicable standards. Common grounding methods include connecting the shield to a ground bus or grounding electrode system. The grounding connection should be made with a low impedance conductor to minimize the voltage drop between the shield and ground. The grounding conductor should be sized according to the requirements of the NEC. In addition to grounding the shield at the source end, it may also be necessary to ground the shield at the load end. This is particularly important for long cable runs, where the voltage drop along the shield can be significant. Grounding the shield at both ends helps to equalize the voltage and minimize the risk of circulating currents. Now let's discuss cable testing. After the cable is installed and terminated, it should be tested to ensure that it is functioning properly. Common cable tests include firstly, insulation resistance test. This test measures the resistance of the cable insulation to verify that it is free from defect. Secondly, high potential test. This test applies a high voltage to the cable to verify that it can withstand the system voltage. Thirdly, time domain reflectometry, or TDR test. This test uses radar pulses to detect any faults or discontinuities in the cable. Fourthly, partial discharge test. This test detects any partial discharges within the cable insulation, which can be an indication of impending failure. These tests should be performed by a qualified electrician using calibrated test equipment. The test results should be documented and compared to the manufacturer's specifications. If any problems are detected, they should be corrected before the cable is put into service. Let's discuss maintenance and inspection. Regular maintenance and inspection are essential for ensuring the long-term reliability of the medium-voltage cable system. The maintenance program should include the following. Firstly, visual inspection. The cable and termination should be visually inspected for any signs of damage such as cracks, cuts, or corrosion. Secondly, cleaning. The cable and termination should be cleaned regularly to remove any dirt, dust, or contaminants. Thirdly, tightening. The cable connections should be tightened periodically to ensure that they are secure. Fourthly, testing. The cable should be tested periodically to verify that it is still functioning properly. The inspection and maintenance schedule should be based on the manufacturer's recommendations and the operating conditions. Any problems that are detected during inspection or maintenance should be corrected promptly. In addition to the technical considerations, it is also important to consider the cost implications of using medium-voltage shielded cable. Shielded cable is typically more expensive than unshielded cable. However, the additional cost may be justified by the increased reliability and protection that it provides. The cost of cable termination can also vary depending on the type of connector used. Cold shrink connectors are typically less expensive than slip-on connectors. However, slip-on connectors may offer better performance and reliability in certain applications. The cost of labor for cable installation and termination should also be considered. Installing and terminating shielded cable can be more time-consuming than installing and terminating unshielded cable. Therefore, it is important to obtain accurate cost estimates from qualified electricians before making a decision. Finally, it is important to remember that electrical safety is paramount. Medium-voltage electrical systems can be dangerous, and it is essential to take all necessary precautions to prevent accidents. Only qualified electricians should work on medium-voltage electrical systems. All work should be performed in accordance with applicable safety standards and regulations. Personal protective equipment, or PPE, such as gloves, safety glasses, and arc flash suits, should be worn at all times. The electrical system should be de-energized and locked out before any work is performed. Warning signs should be posted to alert others to the presence of energized equipment. By following these safety precautions, you can minimize the risk of electrical accidents and ensure the safety of yourself and others. In conclusion, the decision of whether or not to use medium-voltage shielded cable for a 4160 volts transformer application depends on a number of factors, including the proximity to other cables, the electromagnetic environment, the risk of mechanical damage, and the applicable standards and regulations. While shielded cable is not always mandatory, it is highly recommended in situations where there is a risk of electromagnetic interference or mechanical damage. When stress cones are not feasible, cold shrink connectors or slip-on connectors can be used as alternative termination methods. However, it is essential to consult with the transformer manufacturer and a qualified electrician before making any modifications to the transformer or selecting a termination method.